Renewable power is booming, as innovation brings down costs and starts to deliver on the promise of a clean energy future. Renewables are increasingly displacing dirty fossil fuels in the power sector, offering the benefit of lower emissions of carbon and other types of pollution. There are several ways to generate energy from renewable sources, but one of the most common methods is solar power. Solar power is the key to a clean energy future. Every day, the sun gives off far more energy than we need to power everything on Earth. Today, more and more homeowners realize the advantages of a solar panel system installation in their home. However, many people find themselves overwhelmed with the inherent limitations available, making it difficult to decide whether or not it would be beneficial to install solar panels. Scientists have revealed a new type of solar cell that revolutionizes the renewable energy industry, known as perovskite. What is perovskite, and what makes it far better than standard solar cells? Today, we'll look at the game-changing perovskite solar cells that have the potential to change the whole solar energy industry. But first, we are giving away $100 to one of our lucky subscribers. All you have to do is watch the entire video, leave a comment with your greatest takeaway, like, share, and subscribe. So, without further ado, let's get started. With the growing threat of climate change due to the excessive release of carbon emissions, many nations are looking to clean energy alternatives to replace traditional fossil fuels. The most established low-carbon energy technology, along with wind, is solar photovoltaic, or PV, and as it grows in scale, the development costs are decreasing. The total cumulative installed capacity at the end of 2019 amounted to around 627 gigawatts globally, with an average of 125 gigawatts of new capacity anticipated worldwide between 2021 and 2025. Solar is on track to break records for new global deployments each year after 2022. According to the International Energy Agency, solar PV generation increased by 22% in 2019, ranking second among all renewable technologies in absolute generation growth, after only wind but ahead of hydropower. China is the world's largest consumer of solar energy. In 2019, the country installed 205 gigawatts of solar panels and generated 223.8 terawatt-hours of solar energy. The Huing Hydropower Hainan Solar Park, with 2.2 gigawatts of installed capacity in Qinghai Province, was the biggest single solar project at the time. In 2019, the United States has the world's second largest installed solar capacity, reaching 76 gigatons and generating 93.1 terawatt-hours of power. However, as the US ramps up its renewable energy efforts and aims to completely decarbonize its power system by 2035, the country's solar installations are expected to reach over 419 gigawatts over the next 10 years. Solar energy provides a lot of advantages, since solar energy doesn't need an external supply to function. Its maintenance and energy production expenses are almost zero. The production and installation of the components are the only costs associated with the use of solar energy. As a result, the installation is quickly recovered as there are no extra expenses related to its usage. Additionally, since the main source, the sun, is almost always available, there is no fluctuation in the cost. Solar energy also reduces energy loss during long-distance transportation. The performance of the installation in densely populated areas is impacted by losses during the transport and distribution of energy, which grow with the distance between the production and supply points. On the other hand, the distances are significantly cut down with the individual installation of solar panels on roofs, improving the electrical system's efficiency. Due to their ease of installation, PV panels may be placed practically anywhere, making use of both vertical and horizontal areas that have no specific purpose. This refers to the capability of supplying energy in distant areas where the expense or impossibility of constructing electrical distribution lines. Another benefit of solar energy in urban areas is that it doesn't produce noise pollution, because it doesn't need maintenance and has a far longer lifespan than other energy production systems. It also doesn't produce any waste. However, PV panels have drawbacks, limiting their capacity and applications. One of the most important is the cost. The quantity of solar array panels required to collect energy for an entire home often costs tens of thousands of dollars, making the electricity produced far more expensive than that provided by conventional power sources. Also, the size of the system is dependent on your available space. Available space is a big factor in solar panel installation because, If your roof is not big enough, for example, you may have to downsize your system or rethink getting solar altogether. Solar panels are still fairly large products, meaning they require a big space to be installed. The size disadvantage means that they cannot be placed in small areas and actually require a large roof. Another factor to consider is that the expansive battery banks required for solar arrays are often not covered under the warranty for the panels themselves. A big solar array is needed to power an entire building. Unfortunately, photovoltaic technology is still in its infancy. Therefore, we must build large arrays to compensate for the inefficiency of single panels for now. A bulky mechanical orientation solar energy is reduced by overcast ski system may also be required to turn the panels as they follow the sun across the sky. Batteries, too, can take up a fair amount of space. Solar panels, like anything else facing the sun, are eventually harmed by ultraviolet radiation. Rain, snow, dirt, temperature fluctuations, hail, and wind are all harmful. A few of the more notorious substances contained in panels and associated equipment include: toxic batteries are required by solar arrays. Cadmium. When sealed inside solar panels, cadmium is harmless. Cadmium may cause serious environmental damage if it leaks from the panel. To prevent this carcinogenic material from leaching into soil and water, panels must be disposed of with extreme care. Although solar panels provide clean, renewable energy, the manufacturing process may be harmful to the environment. Solar panel mass production may result in the use of fossil fuels and the generation of plastic waste. They are just not environmentally friendly to mass produce. However, a new material for making solar panels promises to fix most of these problems. You can call it the holy grail of solar energy because of its versatility. The breakthrough material is known as perovskite. What is perovskite, and how does it work? Perovskites have the potential to be used to make solar panels that can be readily deposited onto most surfaces, including flexible and textured ones. These materials would also be lightweight, inexpensive to produce, and as efficient as today's top solar materials, which mostly consist of silicon. They are the focus of increased study and investment, but companies seeking to capitalize on their potential must address a few remaining challenges before perovskite-based solar cells can be economically viable. The name perovskite refers to a family of compounds rather than a single substance, such as silicon or cadmium telluride, which are other strong rivals in the photovoltaic realm. The perovskite solar material family is named after the mineral perovskite, which was discovered in 1839 and named after Russian mineralogist Alekseyevich von Perovski. A perovskite solar cell is a form of solar cell in which the light harvesting active layer is a perovskite structured compound, most commonly a hybrid organic-inorganic lead or tin halide-based material. Perovskite materials, such as methylammonium lead halides, are inexpensive and straightforward to produce. Perovskites have unique advantages such as a broad absorption spectrum, fast charge separation, long electron and hole transport distances, long carrier separation lifetime, and others, making them highly promising materials for solid-state solar cells. Without a question, perovskite solar cells are the rising star of photovoltaics. Their capacity to absorb light over practically all visible wavelengths, exceptional power conversion efficiencies that have already exceeded 20% in the lab, and relative ease of fabrication are prompting enthusiasm in the solar power sector. Perovskite PVs offer a significant advantage over conventional solar technology in that they can respond to different wavelengths of light, allowing them to convert more of the sunlight that reaches them into power. Furthermore, they provide flexibility, semi-transparency, tailored form factors, lightweight, and other advantages. Electronics designers and researchers are certain that such features will enable solar cells to be used in a plethora of new applications. For example, perovskite cells can power small Internet of Things gadgets and even aircraft where they are not expected to last very long. Perovskite solar cells have the potential to revolutionize the solar energy industry due to their inexpensive production costs and power conversion efficiency that is comparable to existing commercial offers. Despite these credentials, perovskite solar cells have failed to make the transition from the lab to solar farms. One limitation of the technology is the ease with which perovskite solar cells degrade in the environment, as shown in lab studies. This property significantly reduces their working lifespan. Although Di Carlo of Tor Vergata University of Rome and colleagues have now investigated the lifetime of perovskite solar cells in a real-world situation using the world's first standalone PSC solar farm. The solar cells worked effectively for 9 months until failing unexpectedly due to issues with each cell's encasing box. The results gave a roadmap for improving the technology and bringing PSCs one step closer to commercialization. Researchers have long been aware of the issues with PSCs and have been attempting to improve the technology's resilience. According to research, degradation may occur when ions travel across the layers of a cell, which is one cause that affects cell lifespan. Incorporating 2D materials inside a PSC, such as graphene, has been proven to reduce these effects, and the material has already been used to prolong PSC lifetimes from a few minutes to several months. Researchers discovered that adding graphene flakes to a cell significantly increases its energy conversion. DiCarlo and colleagues constructed 9 graphene perovskite cell panels to investigate the whole effect of graphene addition. Each cell featured a 9-layer structure that included a perovskite sheet and graphene-doped titanium dioxide sheets. The layers were protected by gold, a conducting substance known as poly, and fluorine-doped tin oxide sheets. The construction was then encased in a glass-topped box using ethylene vinyl acetate as an encapsulant. Each final panel has a surface area of 0.5 square meter. The panels were installed in 2 parallel rows on the site of Hellenic Mediterranean University on the Greek island of Crete, and their energy was utilized to power one of the university's laboratories. The yearly average solar irradiation at this location is 1990 kilowatt-hours per square meter. This tiny solar farm was built with a maximum power point tracker, a device that extracted the farm's highest electric power output, as well as a weather station to monitor environmental conditions. On June 10, 2020, the team started monitoring the solar farm, collecting data at least twice a week. For the first 9 months, they measured the farm's highest output to be 267 watts. However, on March 2, 2021, the farm's capacity to generate electricity suddenly decreased. The presence of oxygen and moisture inside each panel, which physically harmed its multiple layers, caused this failure, according to cell analysis. According to DiCarlo and his colleagues, the oxygen and moisture entered the panels through gaps that developed in their encasing boxes. These gaps opened the inside layers of the panels to the elements. The researchers think this failure was caused by heating effects. The data show that the cells were exposed to temperatures as high as 158 degrees Fahrenheit, which is close to the temperature at which EVA deteriorates. The results provide a series of rigorous testing of a novel solar cell technology, says Mark Jacobson, a Stanford University professor of civil and environmental engineering whose research focuses on renewable energy technologies such as solar cells. Despite the cell's eventual failure, Jacobson feels the results are an essential step toward commercializing PSC technology. He points out that the adoption of a specific solar technology is dependent on a variety of factors, including cell efficiency. This work will likely contribute to the continued decrease in cost of solar photovoltaic panels. He adds, DiCarlo and his colleagues are currently investigating other methods to enclose their graphene perovskite cells so that the panels can survive temperatures of up to 248 degrees Fahrenheit, which is far higher than projected operational conditions. The company thinks that by making this change, their panels will function better in real-world conditions. We've shown that graphene can be utilized to enhance cell properties not just in laboratory cells but also in actual panels used in solar farms, adds DiCarlo. Now, he says, all they need to do is increase the lifespan to fit commercial uses, which he expects will happen within the next 3 to 5 years. On the commercial side, Sol Technologies has signed an investment deal with Hideo Sawada, a Japanese investment company. Sol's goal is to merge perovskite solar cells with other existing goods, and this financing agreement comes only a year after the company was founded. Sol has developed sunbreaker lamellas using perovskite solar cells. The product would be marketed across Europe before potentially expanding to the rest of the world. It is also stated that a perovskite photovoltaic cell manufacturing line has begun in Guizhou, Zhejiang Province, East China. Microquanta Semiconductor is said to have funded the 40-hectare factory, which is intended to generate more than 200,000 square meters of photovoltaic glass in a year. Let's hear what you think of perovskite PV cells in the comments section below, and thanks for watching the video. If you want to continue to learn about everything regarding future technologies, we've got 2 more video options for you on the screen to check out. And don't forget to give a thumbs up on this video if you liked it and subscribe to our Electric World channel for daily content just like this.